Modern software engineers feed strict prompts into AI, expecting deterministic logic. Instead, they receive probabilistically generated code. When that generated code inevitably breaks in a production environment, the industry overwhelmingly diagnoses the failure as an AI hallucination. The standard reaction targets the generator. Engineering teams tighten system guardrails, expand context windows, or simply stall their product roadmaps, waiting for the next smarter model iteration to arrive. Hamza Abdullah's Software Development Prompting Framework, SDPF, offers a different diagnosis. What the industry calls hallucination is actually specification-induced speculation. When an architect writes an incomplete contract or relies on unverified facts, the specification contains structural gaps. The AI model bridges that missing logic with its best statistical guess. Upgrading to a more capable model does not solve the root error. Better models simply generate more plausible, harder-to-detect guesses. SDPF shifts the focus from refining the generator to hardening the acceptance criteria. To control AI output predictability, we have to stop demanding deterministic behavior from a stochastic model. The solution is enforcing a deterministic specification. This raises an architectural paradox. You cannot extract mathematically reliable software from an engine built entirely on statistical probabilities. SDPF resolves this contradiction through a principle called bounded stochasticity. The framework moves away from dictating how the AI should write the code and focuses instead on what the output must compute. Without boundaries, an AI wanders an infinite stochastic output space. SDPF limits this using structural invariants, collapsing infinite possibilities into a specific acceptable subset. Inside this boundary, the model freely varies internal choices. Conversely, code generated outside these invariants is automatically rejected. There is a specific vulnerability that structural invariants alone cannot catch. AI models fluently assert stale facts, like deprecated API endpoints, dead command line flags, or outdated Python versions, matching from historical training data. A flawlessly structured specification will still produce catastrophic failures if it is built on top of incorrect assumptions about the deployment environment. To neutralize this threat, SDPF mandates core principle 2, the technical verification gate. Operating as a pre-execution gate, the TVG blocks progress before any code is generated. A standard TVG entry requires 4 components: the target asset, a verification command, a pass condition, and a halt rule. The framework executes this command against the live environment. If the system returns a mismatched version, the halt discipline physically severs the pipeline. The architect faces a forced resolution. They must either update the target environment to match the specification or rewrite the specification to reflect the reality of the environment. Traditional engineering cultures often shim mismatches or silently downgrade versions just to turn the build green. SDPF rejects that compromise. The TVG enforces a mapping between the generated system and the actual world, neutralizing the risk of a model relying on imagined training data. If we zoom out, the default power structure of the AI industry is clear. Control concentrates heavily at foundation model labs and hosting platforms. Software engineers are pushed downstream as passive consumers. The SDPF methodology structurally disrupts this arrangement by making the specification, rather than the model, the sole authoritative artifact. The framework strips away vendor leverage by completely separating the system's behavioral logic from the underlying AI model. Because the specification tests against structural invariants rather than syntax, the architect can swap out Claude, GPT, Gemini, or Llama without rewriting the contract. The hosting platform is reduced to replaceable operational scaffolding. It enforces the specification, but it has no power to dictate it. Authority concentrates on the human architect. They determine acceptable inputs, define processing logic, bound permitted outputs, and dictate failure states. But this authority carries a dark side. The architect assumes total, inescapable accountability for the deployed system. The framework eliminates any avenue to deflect blame onto a model or a platform. Under SDPF, the capacity to write a precise, model-agnostic contract defines how the deployed AI system will behave. This rigorous chain of accountability answers the ultimate question for enterprise deployment. How do you prove to an external auditor that a stochastic system operates safely? Historically, highly regulated sectors like medicine, aviation, and finance have been structurally blocked from deploying AI because they lacked a mechanism for empirical evidence. An SDPF evidence package includes a locked specification base, test suites, and an implementation hash. Every code function contains a unique REQ ID, linking logic directly to business requirements for unbroken traceability. Finally, a cryptographic provenance signature seals the artifact, rendering it completely tamper-evident. For regulatory auditors at the FDA or the FCA, this package delivers exactly what they require. It provides empirical, mathematical proof of intent, execution, and verification. The macro impact of this shift on the developer labor market is severe. When the AI mechanically executes the contract, the actual act of writing code ceases to be a scarce or valuable skill. The future bottleneck of software engineering is specification discipline. The most critical operator in the AI era is the architect, the person who can define the boundaries of a system